Okay, everybody, so welcome back to our unit on trig from a rigorous standpoint, and this is part 4. So just to review quickly, in the last video we established the following properties of the functions capital C and capital S. First of all, there was the Pythagorean identity. Secondly, there were the values of those functions at 0. Thirdly, we had the parity laws. Basically say that capital C is an even function and capital S is an odd function. And then finally we had the addition laws, which give the value of capital C at a sum of two numbers in terms of the values of C and S at the individual numbers. So if we have two numbers, theta and phi, both real, we can calculate capital C of theta plus phi if we know capital C of theta and capital C of phi individually, as well as capital S of those two numbers. Okay, and then we can add to this also the idea that we have Euler's formula. That was e to the I theta equals C of theta plus I S of theta. And we can also add the geometric interpretation. Because we had a precise theorem about that as well. Right? And the precise theorem says that the arc length of the arc of the unit circle from 1 to e to the I theta is the absolute value of theta if you understand arc length appropriately. You have to understand it as the limiting length of what I call a raveling, whose endpoints approach e to the I theta along the unit circle. Okay, so anyway, we have that. We talked about that theorem as well. All right, so to go further with our analysis, we need some sort of estimates now. And I'm going to begin with this estimate that capital S of theta is less than theta and also greater than theta minus theta cubed over 6 when theta is a positive number that is less than 4 root 5. Okay, pretty strange constant 4 root 5 that appears here. You'll see where it comes from when we do the proof. All right, and then as a corollary of that, once we establish that theorem, you see that because theta is positive, we can divide through by theta without changing the inequalities, without changing the direction of those inequalities. And so if you divide through by theta, here's what you get: 1 minus theta squared over 6. Right? Then in the middle you'll have S of theta over theta, and then here you'll have a 1. And you see that, okay, this can be rearranged in the following way. Okay, so equivalently, we can write these inequalities this way. Okay? And this makes it clear that, so we can state as like a second corollary, that S of theta over theta approaches 1 as theta approaches 0. Because you see that if I let theta go to 0, and at the moment we're just talking about theta going to 0 through positive values, because I'm restricting theta to be positive in this original theorem. So let's assume theta is some small positive number that's like moving towards 0. Okay, so as that happens, look what happens to this bound. This bound will go to 0 as well, because if theta is going to 0, then certainly theta squared is also going to 0, and therefore theta squared over 6. But then you have a 0 on this side, so the squeeze theorem will tell you that the thing in the middle has to go to 0 as well, right, as a conclusion from the squeeze theorem. But since 1 is a constant, that just tells you that S of theta over theta is getting closer and closer to that constant, since their difference is going to 0. So S of theta divided by theta is approaching 1 arbitrarily closely as theta goes to 0, at least if theta is positive. Right? But then you see that if theta were negative, we could do the following trick. Let's say we had some negative theta that was also approaching 0. Okay? Well, what we can do then is we can just consider minus theta, which is on the positive side, and will also be approaching 0. And because the sine function is odd, you see if I take this ratio and I just multiply top and bottom by minus 1, nothing changes. But because the sine function is odd, you can pull the minus inside. And now you see that we've reduced it back to the positive case. To be even more explicit about it, if I call negative theta like phi, which is positive, then this just reduces to S of phi over phi. Right? The bottom being phi also. And then since phi is positive, it like comes back to the last case. the positive case. And we know already that in that case, we do get something that is going to 0. So you see that whether theta approaches 0 through positive values or whether it approaches 0 through negative values, it makes no difference because of the oddness of the sine function, which allows us to take this minus here and pull it inside. But yeah, in both cases, we have this conclusion. All right, now, I've been concealing something this whole time in talking about this corollary, and it's time to really have an honest accounting of this issue. I said that theta is approaching 0, right? But we never really defined anything like that. You see, we've only ever talked about limits of sequences. The only kinds of limits we've ever encountered in our course so far, in any rigorous way, is the limit of a sequence, right? And there's no sequence here. There's no sequence here. Theta is supposed to be approaching 0 through, like, moving continuously, moving gradually, continuously, achieving every position between its current position and 0. So it's not like a sequence of values. The sequence jumps. The sequence jumps from one point to another to another. But there's no jumping here. There's only like continuous motion. So this is a different type of limit process. When I write these convergence arrows, it's referring to a different type of limit process. They're not sequential limits. That's what's called functional limits. Okay? So we haven't discussed functional limits in any formal sense. So therefore, in order to avoid that whole issue, but yet still get a technically correct theorem, so I can't leave this corollary the way it is right now, because in this corollary I'm using this notion of functional limits, which we haven't defined. And obviously you can't write down a theorem that contains terms or expressions that you haven't yet defined. It's not valid to do that. So I'm going to just avoid the entire issue by just rephrasing the theorem in this way. I'm going to say that if I have any sequence of theta values that approaches 0, imagine you have, instead of theta moving continuously towards 0, you just take some sequence, theta 1, theta 2, theta 3, that approaches 0. So we understand what that means because we know what it means for a sequence to approach something. We define sequential limits. So yeah, we know what it means for some sequence, okay? And then so let's phrase the corollary this way. If I take any sequence whatsoever that approaches 0, as n goes to infinity, and I plug those numbers into the capital S function and then divide by those very same numbers, that will approach 1. Again, as n goes to infinity. Okay, as long as the sequence inside, the theta n sequence, goes to 0. And that's a way of formulating the same basic phenomenon without referring to functional limits at all. This way of saying this corollary only refers to sequential limits. This is a sequential convergence statement, and then this one is also a sequential convergence statement. And now I phrase the theorem as a conditional. The whole theorem now is a conditional statement. If this convergence statement holds, then this other convergence statement here will hold as well. And you see that the way you would deduce that is by taking the inequalities here in this red box and just substituting theta n for theta. Right? If I substitute theta n everywhere there's a theta, then since theta n is going to 0, then theta n squared will also go to 0, and then theta n squared over 6 will go to 0. So the squeeze theorem still applies. This will go off to 0, and then this quantity in the middle here will also approach 0. So we'll get the correct conclusion. Right, but that's just a way of reformulating that corollary to avoid any mention of functional limits where the theta moves continuously, and just restrict all convergences to sequential convergences. But the cost is that you have to phrase it as a conditional. That if you have this sequential convergence, then you have this other sequential convergence as well. Okay, anyway, so it all boils down, this whole sequence of corollaries here boils down to proving these bounds. I apologize for the howling of the beagle there. That's my neighbor's dog, and she does that periodically. So, sorry. Okay. Where are we? Yeah, let me just make a couple more comments. First of all, there's something I omitted from this corollary, which is that the same conditions on theta have to be true. Let me just erase some of these pictures here. In fact, maybe I should just rewrite this or statement. So we have these inequalities here, or Another way to rephrase those is 0 is less than this is less than this. Okay? But there's still this clause, when theta is positive and less than 4 root 5. Because essentially this corollary here is just a rephrasing of this theorem. They're not significantly different. It's just a reorganization of that theorem, where the inequalities are just written a little bit differently. Right? We took that theorem, we divided through by theta, and since theta was positive, the direction of the inequalities was unaffected. Right? And then we just reorganized by adding terms to both sides or subtracting terms from both sides or whatever. So the same condition has to apply. It's just the same theorem, really. These two are virtually the same theorem. So the same condition applies. This only works when theta is in this range. And so this theorem has the same restriction. So I wanted to make sure I was clear about that. That's part of that corollary. Now, you may also wonder what happened to the 4 root 5 when we reached this corollary here. That doesn't make any appearance in that statement, that conditional statement. And the reason it doesn't is because if I assume that theta n goes to 0, let's say I assume that theta n is some sequence that approaches 0, well then eventually it's going to get less than 4 root 5, right, on its way towards 0. I should draw a little picture. So basically I'm assuming theta n is approaching 0, right? And of course that also means that the absolute value of theta n is approaching 0. And that's happening on the positive side only, because absolute values are non-negative by nature. So as the absolute value of theta n approaches 0, it's eventually going to get less than 4 root 5. So it could start over here. Like, let's say absolute theta 1 is here. Let's say absolute theta 2 is here. But eventually, as it gets closer and closer to 0, it will automatically be less than 4 root 5. Okay? So, okay, and actually now that I'm looking at it a little more closely, I realize that there's also a little bit of an imprecision in the way that I stated this corollary, which is that, okay, the theta n's should not equal 0 ever, right, because I'm dividing by theta n. So we can't have a 0 in the denominator. So what I really should say is that theta n is approaching 0, but theta n is never equal to 0. For all n. See, otherwise the statement wouldn't even make sense, because you can't divide by 0. So to get a really precise statement, it's that. Okay. So yeah, we're assuming two things. We have a sequence of values, theta n, which is going to 0, but none of them is equal to 0. And then we have to conclude that capital S of theta n divided by theta n approaches 1. Okay, so yeah, notice that in this picture again, since the theta n's are never equal to 0, the absolute values of the theta n's are actually strictly positive. So we have a sequence that's like strictly positive, so on this side of 0, but not equal to 0. And then eventually it does get less than 4 root 5. So again, it may not begin less than 4 root 5. The first few terms may be greater, but on its way towards 0, it has to eventually get less than 4 root 5. Okay, and once it does, then these bounds apply. Or to put it differently, these bounds here apply. And then the rest of the argument goes through exactly as we said here, right? The theta n's are going to 0, their squares are going to 0, their squares over 6 are going to 0, and then the squeeze theorem takes over. All right, so the proof does work. Now, little subtlety in that is that it's this sequence that we can say is between 0 and 4 root 5, eventually, meaning for all large n. For all n, like, sufficiently large. And it's only sufficiently large n that matter anyway, because remember, we're only concerned with what's happening as n goes to infinity. So it makes no difference at all that there's this restriction, that n has to be sufficiently large. Because all we care about is the behavior as n gets infinite anyway, n gets arbitrarily large. So we just wait long enough for this cutoff to happen, and then we just let n continue growing from there. All right, but what that's going to tell us is really by the squeeze theorem, it's going to give us this. And then it's up to us to see that we can drop the absolute value sign. We can always just drop the absolute value sign. Okay, and here's the reason. If the absolute value, let me say it this way, if theta n happens to be positive, then the absolute value of theta n is just theta n. So the absolute value sign is redundant anyway. In both places, you can just drop it. But if theta n is negative, remember, none of the theta n's is equal to 0. So every one of them is either positive or negative. Okay. Yeah, in the negative case, then the absolute value of theta n is just minus theta n. So this quantity here, what does it become in that case? Right? It's either just this directly when theta n is positive, because you can just literally drop the absolute value sign according to this. Or, in the case when theta n is negative, it would be this, according to this identity here. So this is the case when theta n is negative. Right, but notice that because the sine function is odd, it lets the minus sign through. And then the two minus signs just cancel out from the top and the bottom. So in both cases, you end up just getting the same expression. And that covers all possibilities. So basically, in all cases, the expression in this red box, which is the thing we really know goes to 1 by the squeeze theorem, since we have the correct range. But that expression in the red in that heavy red box can always be rewritten in this way. And therefore, it's correct to conclude that this expression approaches 1, too, simply because these two expressions are exactly equal to each other, regardless of whether theta n is positive or negative. Okay. So anyway, that's a complete proof of that sequence of corollaries, but we still haven't proven the actual theorem itself. All right, and that's going to come, obviously, from the definition, the series definition. Let's take a quick look at it. So we know that we have this series expansion. The next term would be like theta to the 5th over 5 factorial, and then theta to the 7th over 7 factorial, which happens to be 5040. Okay, so we have this whole series like that. The next term would be like theta to the 9th over 9 factorial, and so on. I don't know 9 factorial by heart. This 6 here is 3 factorial, and this is 120 is 5 factorial, and this is 7 factorial. Okay. So we can start by doing the following thing. I can basically like group these two terms together here, factor out a minus from both of those terms, and also factor out this. And then what's going to be left is a 1 from that second term, and then a minus, and then like a theta squared over 20. Okay. And then I can also group together like the next pair of terms and kind of play the same game. Factor out a minus, factor out a theta to the 7 over 7 factorial, and what's going to be left is a 1, and then a minus, and then a theta squared over, well, 9 times 8. This 20 is just 5 times 4. Okay, the next thing would be like this, and then a 1 minus theta squared over 11 times 10. And that pattern keeps going, just by grouping the terms like 2 at a time. Okay, so yeah, if you multiply it back, you'll see it's correct. Take this and multiply by 1, it gives you this term here, including the minus sign. But then if you also take that whole thing, including the minus sign, and multiply by that other term, the two minus signs will cancel, giving you this plus. And when you have that in the denominator, you'll have 6 times 5 times 4. That 6 is 3 factorial. So when you multiply by 4 times 5, that's what's giving you 5 factorial, which is the correct denominator that we want in that term. Okay, and similarly, like the 7 factorial in the bottom times 9 times 8 will give you 9 factorial in that term. So anyway, this is all correct. And here's the key observation. If I restrict theta to be in this range, so then theta squared is going to be in this range. Oh, I'm sorry. Did I make a little mistake here? Yes, I did. Sorry, it shouldn't be 4 root 5. It should be 2 root 5. Let's go back and fix that everywhere else. I just misremembered what that number was. Okay, it's actually 2 root 5, and here as well. Okay, wow, you can see where it comes from is that when you square that number, what do you get? 4 times 5, which is 20. And that 20 is exactly this denominator right here. That's where it's really coming from. So what do we infer from this is that theta squared over 20 is between 0 and 1. And therefore 1 minus theta squared over 20 is also between 0 and 1. Okay, yeah, in general, if I have a number u that's between 0 and 1, then 1 minus u has the same property. It's also between 0 and 1. It's easy to check that, so I'll leave it to you to check. It's like geometrically speaking, it's like this. If you take some point u between 0 and 1, 1 minus u is this distance. And that's also between 0 and 1. As a distance, it's positive, but it's less than 1, so, okay. Anyway, so we use that here and we get this. Now 1 minus theta squared over 20, this quantity right here, is exactly what you see in brackets there. So that's positive and less than 1. Okay, but the key observation is really just that it's positive. That's the thing we really want. That's positive. But now there's another crucial observation too, which is that I claim that all these other factors in parentheses are even bigger. The things that I just underlined in green, and that continues on forever, like in every one of these groups, all those terms that are underlined in green, they're all even larger than this positive number that I just underlined in blue. So in other words, the thing I underlined in blue is positive, and these green things are even bigger than that, so they're positive too. So I'm going to infer that this green thing is positive, and then this green thing is positive, all the green things, all those quantities are positive. Okay, and why is that? Why does it work? Well, look, if you compare 1 minus theta squared over 20, which is known to be positive, what about that, which is the next term here underlined in green? Okay, well, dividing by 72, I don't have to write. We don't have to write these numbers out. We can see it already from the factored form. But yeah, dividing by 9 times 8 gives a smaller number for this term than dividing by 5 times 4. So this is smaller, and this one is larger. But then you're subtracting here a larger number from 1. Here you're subtracting a smaller number from 1. So this is larger. And this is smaller. See? When you subtract like a very tiny number from 1, you get something relatively large, close to 1. But if you subtract something bigger from 1, then you get something smaller than that. Okay, so you see how it works. And the smaller this denominator is in general, the larger the whole quantity will be. So for example, in the next term, you're going to have, instead of 9 times 8 in the denominator, you'll have 11 times 10 from here. That's larger than 9 times 8. So therefore, the resulting number is bigger. Okay, so you see what I'm saying here is that already, because I put theta in this range, I can conclude this already. But then, even larger than that is this. And then even larger than that is this. And they just get bigger and bigger as you go. So, okay, they're all positive, every single one of them. Okay, but now you see that they're also. So what we just proved is that all the numbers in the heavy parentheses are positive. All the values in every single term, all the way out to infinity, that appear in those heavy parentheses, they're all positive. But notice that they're also being multiplied by positive values. See, theta cubed over 6 is positive because theta is positive. Similarly, theta to the 7th over 7 factorial is positive because theta is positive. Right? Theta to the 9 over 9 factorial is positive because theta is positive. And then you also have these minus signs. You have this minus sign here, and then this minus sign here, and then this one here, and then this one here. So what's happening is you're starting with the value theta and then subtracting away a bunch of positive quantities. Right? Because everything in those gray boxes is positive, and also everything in the heavy parentheses is positive. But you're subtracting all of those things away from theta. So it's clear that the result is less than theta. Right? By starting with theta and then subtracting away positive quantities, you're ending up with something less than theta. Okay, so that justifies this inequality here. S of theta is less than theta, at least when theta is in this range. Okay? All right, now I should really say something, a little minor technicality in this argument. You may worry that these manipulations may lead us astray, where, for example, I took 2 consecutive terms here and factored a minus sign out of them, and also factored some other stuff. But I have to do that infinitely many times, because I'm doing it for infinitely many groups of 2 terms. And that seems a little controversial, maybe, because it's like I'm performing an algebraic manipulation on an expression, but I have to do infinitely many of them. Actually, you can see that, like, if you start with this series here, this is kind of a famous example from the history of math. There was an Italian monk, Guido Grandi, in I think the 13th century or maybe the 14th century, who discovered this argument that by basically grouping terms together like this, it's just a sum of infinitely many zeros, which should be 0 on the one hand, right? But if you group the terms this way, then it's just a 1 plus a sum of infinitely many zeros, which should be a 1. So basically what Guido Grandi concluded is that this was a new proof of the existence of God, because something is being created out of nothing. Okay? Now, of course, we now know from the modern standpoint that this argument is nonsensical because the original series doesn't converge. 1 minus 1 plus 1. The partial sums don't approach anything. If you look at the partial sums, right, the partial sums go 1, 0, 1, 0. They just oscillate between two values. They don't actually settle down toward any limit. So because of that, this argument doesn't really work. You're not working with convergent expressions here. But still, we might worry that by grouping terms two at a time and factoring stuff out of them, we may be doing something non-rigorous. Okay? So to make up for that, to fix that, you can make the following argument. You can say, do this grouping process very, very far out, but not all the way out to infinity. Just do it extremely far out, and then you'll have like a tail of the original series left over, meaning some tail of the series from some term onwards. But you see that the tails of, in general, when you have a convergent series, you can choose a tail of that series to have a value less than any epsilon, any positive epsilon. You can always find some tail that will have a sum less than epsilon. That's a general fact about series. If I have any convergent series at all, let's say this converges, right? Then I can always find some tail, sufficiently large n, so that this will converge to something like less than epsilon for any epsilon positive, no matter how tiny it is. There exists some cutoff point, capital N, such that if you cut off the series from that term onwards, that series converges to something less than epsilon. Okay, and reason why is because since the original series converges, let's say it converges to this sum, so the full sum of the series. Okay, so then if you look at A minus the nth partial sum, right, that's like the, and then let me take the absolute value. So that's the full sum all the way to infinity minus the partial sum up to term capital N. And that just gives you exactly that tail. Well, it's not exactly that tail. It's like term n plus 1. But it doesn't matter. I can call that term n plus 1, whatever. Okay, but notice that this is going to 0 because the partial sums of the series are converging to its full sum. So you see the tail, the absolute value of that tail is going to 0 as big N increases. Big N. So by choosing big N large enough, I can make the absolute value of this tail as small as I please. So I have here a convergent series. We know that the series for S of theta is convergent. So I can choose a tail of that series whose sum is less than this first positive term, this entire first positive term here that was subtracted off. Okay, so the reason why I choose it that way is because then by subtracting off that thing in that big gray box, whatever the value of this tail here is, it can't make up for that subtraction. It's too small in that. Its absolute value is already less than that subtracted off term. So that tail can't make any difference to the sign of the answer. Or, well, can't make any difference to the sign of the number in the gray box. The number in the gray box is positive, but we're subtracting it away. And then by adding back this tail, it's not big enough to make up for that. And then you see that the rest of the terms that were subtracted off are also positive terms that were subtracted off. So the argument still works. You started with theta. We subtracted off some positive number, but then the tail might partially cancel that out because that tail may be positive. But the point is that that tail is small positive number, so it's not big enough to fully make up for the subtraction of that first term. And then I'm also subtracting a bunch of other positive terms. So clearly I still have something that's less than theta. And it doesn't require us doing this factorization process infinitely many times because we can stop when we reach this tail. Okay? So that's like a rigorous version of that argument. You basically factor by twos, right? You group by twos and you factor for a long time, but you stop when you reach that tail. And that tail here is chosen specifically to have a value that is an absolute value less than this first subtracted number. Okay, so that avoids the need for doing that grouping by twos thing sort of infinitely many times. Okay, anyway, that's the rigorous version of that argument. Good, so, okay, what have we established so far? We've established only this upper bound. Okay, and now I want to look at this lower bound and establish that one too. And the argument is virtually the same, so I'm not going to go through the full argument. I'll just sketch it for you. Right, so once again, you just start with this series. All right, and then what we're going to do is just like group by 2's again, but just starting from a different point. All right, so you see the argument this time is going to be that everything that we're adding here is positive. So we're starting with this quantity and just adding a bunch of positives to it, which makes the value greater than that quantity. The whole thing is then greater than this initial pair of terms, because it's that initial pair of terms plus a positive number, plus another positive number, plus another positive number. Okay, but the key is just seeing that all those things are positive, right? So let's look at the first one. The first group looks like this. We have to show that it's positive. So we'll factor out theta to the fifth over 5 factorial. And that gives us this. Right, and that's going to be positive as long as theta squared is less than 7 times 6. In other words, theta is less than, because theta is positive, theta is known to be positive, because I put it in this range already. So we can just take square roots. We don't need an absolute value sign. The absolute value sign, in other words, would be redundant anyway. But it's like, then you have the square root of 7 times 6. But, so in other words, provided that's true. Provided this is true. That's the question. Is it true? If it is, then this factor here will be positive. And of course, this factor is definitely positive, because theta is already positive. If theta is positive, then so is theta to the fifth. And therefore, so is theta to the fifth over 5 factorial. So there's no question that this factor here is positive. No question at all. But as long as this is true, and the question is it true? As long as theta is less than that number, then this will also be positive too. And then the product of two positives is positive. So at least we'll have proven that that term is positive. Okay. Well, is this true? The answer is yes, because in fact we know that theta is less than 2 root 5. And 2 root 5 is less than root 7 times 6. Right? Because the square of this is 20, whereas the square of this is whatever it is, 42. So it's clear that since we know already that theta is less than this, the smaller number, then it's also automatically less than the bigger number. So yes, the answer is yes, and everything goes through, and it works. Okay, now we still have to see that like this next term is positive as well. But it's the same kind of argument as before, where these numbers in the heavy green parentheses just get closer and closer to 1. Because, for example, the next group of terms would have theta to the 9 over 9 factorial, and then 1 minus theta squared over 11 times 10. But you see that this number is closer to 1, so it's bigger than this previous number. Reason is because dividing by 11 times 10, dividing theta squared by 11 times 10 produces something smaller than dividing it by 7 times 6. And then that smaller thing is being subtracted from a 1, so you get a bigger thing. So yeah, this quantity is even bigger than the previous one. But the previous one is already known to be positive, so therefore this one is also positive. Okay, so yes, all the terms are positive, all these groups. So it's the same type of argument, all right? And that establishes this lower bound for S of theta under the same conditions, same range for theta. This lower bound now has also been established. Okay, so that proves that theorem. That also, all the corollaries that we talked about, right, follow from it. Good. Okay, and then another thing that follows from it, also as a corollary, is that if theta is positive and less than root 6, it so happens, then S of theta is definitely positive. Now, I want to just say one thing. Like, this S function is going to be the sine function. It's going to turn out. And we know from previous experience what the sine function looks like graphically between 0 and 2 pi. And we know that it's positive between 0 and pi, actually. Pi being about 3.14. So in this range here, the sine function is, the capital S function is actually positive in that open interval from 0 to pi. This is a weaker theorem because I'm only saying that the capital S function is positive in the open interval 0 to root 6. Right, which is about 2.45 or something like that. Oops. So that's a smaller interval than this interval, which is about 0 to 3.14. So this statement here, this corollary is weaker than the truth. But it's what's available to us, given what we have so far. We don't really know what pi is yet, anyway. So this corollary is pretty good. 2.45 is pretty close to 3.14. At least it's most of the way there. So, okay, this is going to suffice for us for our purposes right now. All right, and the basic idea is very simple. It's just that we already have a lower bound for s of theta, which holds provided theta is positive and less than 2 root 5. Now, if I can then also force this lower bound to be positive, then s of theta will be positive by comparison. See, and actually even even like less than or equal to 0, greater than or equal to 0 rather, would be okay, because we still have this strict inequality here. So we can still conclude that s of theta is strictly positive, because this is a strict inequality already. So this one can be a weak inequality. That's fine. A mixed, like a weak inequality, greater than or equal. And that's going to mean that this is okay too. Like root 6 is also an acceptable value for theta. But anyway, so we still have to force this to be true. Now, that's pretty easy to do. You see that you can just factor theta out, and then you'll have something like this. And then we want that to be non-negative. Now, theta is positive already, because I put it in this range. I'm restricting theta to be in this range. So we know that theta is positive. And therefore, it all boils down to this factor being positive. And we can make that happen by just making theta squared over 6 less than 1, so that we're subtracting something from 1 which is smaller than 1. And then the resulting difference will be positive. Now, if you multiply through by 6, you get that. And that's equivalent. Like they both imply each other, because 6 is positive. And then in light of the fact that theta is positive, so that we don't need any plus minus sign or absolute value, it's equivalent to say that theta is less than root 6. Well, okay, less than or equal is sufficient, because we don't need this to be strictly positive, we just need it to be non-negative. So we just need that to be like that, okay? So theta does have to be positive, that's why we need this bound here. But then also we need to restrict theta to be less than or equal to root 6, just to make sure that this expression is non-negative. And then by transitivity, right, s of theta is greater than theta minus theta cubed over 6, which is greater than or equal to 0. So by the transitive property, we can just essentially ignore the thing in the middle and conclude that s of theta is greater than 0. Okay, good. Now, one particular result of this, let me call it also a corollary, and we're going to need this soon, is that s of 2 is positive in particular. And that's because 2 is between 0 and root 6. Remember, root 6 is approximately 2.45, or something like that. And, you know, okay, you don't need to know the exact value of root 6 or even anything close to it. All you need to know is that, like, this squares to 4, and this one squares to 6, so there's clearly that relationship. And then you just take square roots on both sides. So, yeah, it's pretty obvious. Okay, and so therefore 2 is like a legitimate value of theta in the preceding theorem. And therefore s of theta has to be strictly positive. Okay. So why do we care about capital S of 2? Well, we're going to use it very soon to prove that s of 4 has to be negative. Okay, and why does that matter? So let's think what we know about the capital S function so far, graphically. I'll put theta on this axis. Okay, so graphically, we first of all, we know that s of 0 is 0, so the graph passes through that point. We established that in the last video. Okay, we also know that s of theta is strictly positive in the open interval 0 to root 6. Well, actually, we can close that interval at root 6, but it's open at 0. So the function starts out positive. We don't know the exact shape of the graph, but we know that it starts out positive in some interval starting at 0, but not including 0, right? And then going up to at least this root 6. But we also now know, okay, and like 2 is somewhere in this interval, root 6 being about 2.45. But 4 is outside this interval. That's not a very accurate picture, but okay, it'll suffice. 4 is definitely outside that interval. 4 is greater than root 6, because this one squares to 16 while this one squares to 6, so you have that relationship. And we're going to prove now that s of 4 is actually negative. So the capital S function takes a negative value at 4. We don't know that value exactly. We just know that it's negative. So it has to pass through that point. Okay. So it passes through some value at 2, whatever it looks like, which is positive. And then it also passes through a negative height at 4. Now, this function is going to be of a certain type. I'll talk about the meaning of that soon. But in general, a Lipschitz function has the property that if it takes a positive value at, let's say, 2, some point, and it takes a negative value at some other point, then it has to take the value 0 at least once in between. So in other words, it's going to have to cross through 0 at some point between 2 and 4. And we're going to take the leftmost such point. You see, because we don't know how many times it crosses through 0. Like in principle, so we don't know very much about this graph yet. So in principle, it could be like very wavy and eventually make it down here. We just don't know. But if it crosses the x-axis like many times, we're just going to take the leftmost of those points. And we're going to call that pi by definition. That's going to be our definition of pi. It's going to be like the smallest positive real root of the capital S function. Pi is defined as the least positive, strictly positive, real root of the capital S function. And we know that such a root has to exist because the capital S function is going to be Lipschitz. And we're going to prove that any Lipschitz function has this property that if it takes a positive height somewhere and then a negative height somewhere else, then it must cross through 0 at least once in between. Right? So now you also might worry, well, what if it crosses through 0 infinitely many times? Like, what if it's like extremely wavy between 2 and 4 and like crosses through 0 actually an infinite number of times? How do I know that there's a leftmost one? Well, the proof is going to make it clear that there is a leftmost one. So we have to await the proof. So we will prove not only the existence of some root between 2 and 4, but also a leftmost root. We will prove the existence, and we'll actually sort of talk about how we locate that. Actually, you've probably encountered this idea before when it comes to polynomials. If we want to find a root of a polynomial, if you can find some value where it takes a positive height and then some value nearby where it takes a negative height, you can sort of zoom in on that root by continuing to test different points and seeing if the height is positive or negative. But we're actually going to be proving that not only is there at least one root between 2 and 4, but there is in fact a leftmost root. Leftmost on the real line, on the theta axis. And it's that leftmost root, that least positive root, that is defined as the number pi. Okay, now notice that this definition is a perfectly good definition of pi, provided we prove all this stuff about Lipschitz functions. But it doesn't tell you how to calculate pi at all. It doesn't give you any method of computing pi to arbitrary accuracy. So we're going to want to think about that later on, just so we have a complete understanding of pi. We should have some computational algorithm, okay, for being able to compute pi to like arbitrary accuracy. In principle, of course, we have limitations on computing power, so even to this day, we only know, I don't know, some trillions of digits of pi. We will never know them all. But at least in principle, with unlimited computational power, we have an algorithm that will continue to spit out more and more and more digits. We want that if we're really going to claim to know that number. All right, so we have a little bit of work to do here. First of all, how do I know that S of 4 is 0? Is negative. This corollary right here. Okay. So it's going to be based on like a double angle formula. You can write 2 theta in the form theta plus theta, and then use the addition rule that we already established. And you see that these two terms we just got are actually exactly the same. We just have 2 of them, so we get 2 s of theta, c of theta. And I'm just going to plug in theta equals 2. So I'll get s of 4 expressed as 2 s of 2, c of 2. And I already know that s of 2 is positive, but I'm going to try to show that c of 2 is negative. And that's going to also prove that s of 4 is negative, because you see that it's the product of 2 with a positive number with a negative number. And such a product is obviously negative. So that's going to give us like the result that we want. Okay. But I need to still prove that c of 2 is negative. All right, so again, we're going to try to use a double angle formula, but this time for the c function. So we like think of 2 theta as theta plus theta, and then it's like cos cos minus sine sine. So that's like c of theta squared minus s of theta squared. And then by the Pythagorean identity, we can replace s of theta squared by 1 minus c of theta squared. So, right, because like s squared plus c squared is always equal to 1. So anytime you see s squared, s of theta squared, you can always replace it with 1 minus c of theta squared. But then if you just simplify that expression, you'll see that you'll get like 2 times c of theta squared minus 1. That's like a famous double angle formula for cosine. Okay, and I'll just plug in theta equals 1. So that will tell me c of 2 will be like 2 times c of 1 squared minus 1. Okay. Now let's look at C of 1. C of 1 is this series. In general, you'll have like theta squared over 2 factorial, but the theta now is 1. And so this would have been theta squared. This would have been theta to the 4th to the 6th. But since theta is 1, all of those just come out to 1. Okay. And well, let me just write in a few more terms. All right, yeah, so this can be evaluated easily. 1 over 2 factorial is 2. So 1 over 2 factorial is a half. 1 minus a half is a half. And then all these terms are positive, you see, by the same type of argument we used before. All these groups of 2 are positive. So C of 1 is certainly bigger than a half. And then if we go back here, see, what do we need? We needed C of 1 squared. That's bigger than a 4th. If you just square both sides, because these are all positive quantities, so you can just, it's equivalent to square both sides. And then multiply by 2, and since 2 is positive, it doesn't change the direction of the inequality, and then subtract 1. And so you get like negative a half. Oops, I realize I just totally messed up that whole argument. No, everything I said is true, but it's not what I need. Sorry, guys. What I really, I guess, want to do is say something like this, like group these two together, and then the next two, and so on. So create the groups of 2 that way. And so that's going to be 1 minus a positive number, then minus another positive number. Okay, so like in particular, whoops, so you're always subtracting off positive numbers. Oh, that's what I mean by these pluses here, just positive numbers. So I can use like the first group as an estimate. That's like 1 minus 1/2 minus 1/24. That's like these 2 terms together. You can just write that as like these first 3 terms together. 1 minus a half plus a 24th. Okay, and that happens to be, let's see, 13/24. If you just work that out over a common denominator, that's 13/24, and then you're again subtracting a positive, subtracting all these positives. So the result is less than 13/24. Okay. Now that's not a very convenient number to work with, 13/24, but the convenient fact that we want is that this is less than root 2 over 2. Let's just take a minute to check that. Which of these 2 numbers is the greater? Well, we can start by just multiplying by 2, because that doesn't affect inequalities. And then we can multiply through by 12, and since 12 is positive, that won't affect anything. Right? And then we can square both sides. And since everything is positive, any inequality between positive numbers is equivalent to the squared version. Okay, and you see which one is bigger. 144 times 2 is certainly bigger than 169. So that must have been the correct sign all along, since the inequalities would have been preserved all along. Okay, so yes, indeed, this is less than root 2 over 2. So we've just proven rigorously that C of 1 is less than root 2 over 2. Therefore, C of 1 squared is less than a half, which is the square of radical 2 over 2. Therefore, 2 times C of 1 squared is less than 1, just by multiplying through by 2. And then 2 times C of 1 squared minus 1 is negative. That's the key insight. Because remember that 2 times C of 1 squared minus 1 is also equal to capital C of 2. And that we've just proven that that's negative. Okay, so yes, we've checked that C of 2 is negative, and therefore we've checked that S of 4 is also negative. So that fully establishes this corollary here. Okay. All right, now we still need to talk about, this idea of a Lipschitz function, and then prove that for any Lipschitz function that takes a positive height somewhere and a negative height somewhere else, there is a leftmost root of that function between those 2 points. And I'm going to just run you through the argument quickly, because this is not really the main track. This technical fact about Lipschitz functions is, not the main line of reasoning here. We want to get back to actual trigonometry. So I'm going to try to kind of run you through this quickly. All right, the first thing, I'm going to just say what a Lipschitz function is. So let's say I have a function like f, whose domain is the reals, and then it also maps into the reals. And to say it's Lipschitz is to say the following thing, that for any value theta in the reals, there exists some h which is positive, and also there exists some m which is positive. okay, such that the absolute difference between, let's say, f of theta and f of phi will be bounded by m times the absolute difference between theta and phi, provided phi is in the interval theta minus h to theta plus h. So what I'm saying is this: if I pick some theta in advance, that theta determines two other numbers, h and m. And h is used to create an interval around theta, centered at theta. And then we just select any other point at all in that interval, phi. As long as phi is in that interval, then we're going to get this inequality. And what this inequality is saying, kind of in spirit, is the following thing. So I'll just draw you a little picture. Let's say the graph of f looks something like this, whatever. And here's my point theta, and here's my point phi. So when you look at the function's height at theta, that's f of theta. And you look at the function's height at phi, that's f of phi. All right, now let's draw this line. It's kind of like a chord in the graph of f, going through those 2 points. The question is, what's the slope of that line? And you just find it by the slope formula, which is like delta y over delta x. Right? The change in the heights between those 2 points is f of theta minus f of phi, because those are the heights of those 2 points. Then you have to divide that by the change horizontally, which is just theta minus phi. And now if I take the absolute value of that slope, what this equation or inequality here is telling me is that the absolute value of that slope is at most m. I'm out of room here. The absolute value of that slope is at most m, as long provided, theta, or phi rather, is in the correct interval. Theta minus h to theta plus h. Right? Because you see that if you just break up the absolute value to the top of the fraction and the bottom, then you can just take the denominator here, which is positive, and multiply it to the other side. And that won't change the inequality, since it's positive. And that produces this inequality here. Okay, so you can reinterpret that inequality, this one, you can reinterpret it by dividing through by this absolute value. And then what it's basically saying is that as long as phi is close enough to theta within a distance of h, so if phi is any point whatsoever, as long as it's within a distance of h from the original theta, then the slope of the secant line between those 2 points on the graph is limited in absolute value by m. Or we can say it without the absolute value sign. The slope of the secant line is limited between m on the one side and minus m on the other. Right, so it basically is giving a limitation to the slope of the secant line. What it's saying is that the graph is not too steep, because for any point theta, there's like a little interval around it where the slopes of all secant lines in there, well, actually, all secant lines of this form, from this point to other points. But all of those slopes are limited between two fixed constants, minus m and m. And now, those constants depend on theta also, just like the h depends on theta. But each theta in the domain comes equipped with such an h and such an m. So that in this interval, around theta, the secant lines that go from this point to every other point on the graph are limited in slope to something between minus capital M and capital M. All right, so that's the basic idea behind a Lipschitz function. Now, I claim that, as a theorem, capital S is a Lipschitz function. All right, we know that its domain is the reals, and that it maps into the reals, so that's fine. Okay? We just need to check that like every point theta has an interval around it where the correct behavior happens. All right? So what we're going to try to look at is we're going to try to look at this type of expression and try to find some bound where, we need to find that m, essentially. Okay, so let's begin by just writing phi as theta plus delta. So delta is defined as the difference. All right, and that's going to take this expression here and re-express it in this way. Actually, maybe I'll make it minus delta. So I'll define delta as this difference here. Doesn't really matter anyway. But the point is I'm just rewriting this phi as like in this form. Okay, and now we can use the sum or the addition rule for the capital S function. It's going to be like s of theta c of delta plus c of theta s of delta. Sorry, my s's and my deltas look similar. All right. Also, this here is an s. It kind of look like a delta. All right. Now we can reorganize this sum. I'm going to take the two terms that both involve s of theta, which are here and also here. Just put those together. Okay, and then I'll just write the remaining term. Oops. Like that. Right now we can use the triangle inequality to kind of break this apart a little bit. We're going to get, absolute s of theta, absolute 1 minus c of delta, and then plus, okay, I'm out of room here, so let me write it up here. It's going to be like absolute c of theta, absolute s of delta. So I'm using the triangle inequality, but I probably should slow this down a little bit. See, I have here like a sum of two terms. You just think of this as a plus sign, but with an extra factor of -1. So it's this plus sign in the middle that I'm breaking off the absolute value. So the absolute value of a sum is the sum of the absolute values. But then also the absolute value of a product is the product of the absolute values. So you see the upper bound can be sort of broken apart as this product, and then plus this product. Okay? Good. Now, delta is up to us. Oh yeah, I don't know how this reappeared. But, oh yeah, so delta is basically up to us to limit. We can limit the absolute value of delta as we please. That's going to be the h. The size limitation on the delta is going to be the h. Because remember that h is like the distance from theta that we can go. So as long as we limit the difference theta minus phi, like less than or equal to h, or maybe strictly less than h, whatever, then what we're just doing is putting phi in a little interval around theta. Okay, by limiting the distance between those two, we're just putting phi in an interval around theta. So basically how the limitation on the size of delta is kind of up to us to control. And let's control it in such a way that it's like certainly less than 1. Oh, is that what I want? Yeah, that's fine. Let me just automatically assume that delta is less than 1 in absolute value. And we may even need to make it smaller than that, but as an initial limitation, we'll take 1 as like an initial limitation. And notice that that's like, less than root 6. And also less than 2 root 5, all those constants that appeared in our various theorems and estimates. Okay, so what that allows us to say is that, for example, s of delta is positive and also less than delta. Because remember that we have this theorem that s of theta is less than theta and also greater than some other thing, provided theta was in this range. So I'm just using that where instead of theta I have delta everywhere. And delta is indeed in this range because, in fact, it's really the absolute value of delta that I want, because delta could be negative. But remember that the absolute value of delta is, well, it's certainly non-negative, and I also chose it to be less than 1. So it is indeed less than 2 root 5. Okay, but so I have some modifying to do. Okay, first of all, I have to modify this to say that it's like s of the absolute value of delta is less than the absolute value of delta. And I also need to modify it to say less than or equal, because you see that delta could be 0, whereas in the theorem, I assume that this number was positive. In our theorem, where we had strict bounds, right, the strict bounds were when theta was strictly positive and less than 2 root 5. But right now, this delta can have 0 absolute value, because delta could be 0. But all that means is that, like, when delta is 0, this will be s of 0, which we know is 0. And this side will also be 0. So the two will just be equal. So I can account for that case by making this a less than or equal. Instead of a strict inequality, which was when theta was positive, in the special case where absolute value of delta is 0, I know that these two sides are equal anyway. They're both equal to 0. So modifying this strict inequality here to be a less than or equal will account for that case. Okay. But I also claim that absolute s of delta is the same as capital S of the absolute value of delta. And that's because s is an odd function. Remember that plus or minus inside doesn't matter. Oh, I'm sorry, it does matter. It just comes out. But if you take the absolute value, then it doesn't matter. Right? So you see that if the number inside is like happens to be minus delta, because let's say delta is negative, so the absolute value will be then minus delta in that case. But then the minus is just going to come out. Yeah, I'd better like handle the details. Yeah, so like imagine that delta is less than 0 and greater than -1. So it's delta's negative, right? Then the absolute value of delta is minus delta, right? And s of that is s of minus delta, and then the minus comes out. But this is positive. No, I'm sorry, it's negative. Because delta is negative. And sine is an odd function, right? So if an odd function is like positive on the positive side, negative on the negative side. Remember, we already proved that the s function. We already proved that the s function is positive on this side, up to √6. And then since it's odd, it's going to be negative on the negative side. Yeah, so the result is positive because you have this extra minus sign here. So because that whole result is positive, it coincides with the absolute value. So that's how it works out when delta is negative. Okay. When delta is positive, it's clear that this is true. Sorry. When delta is positive, it's clear that this equation is true because then all the absolute value signs are redundant. Everything is positive. Right? If delta is positive, then so is s of delta. And that's because delta is limited less than 1. So it's certainly less than 2√5. Or, well, I guess √6 is what I need, right? √6. So yeah, s of delta would be positive in that case. Because 1, right, is less than √6. And the capital S function is positive at least up to √6, we know. And so yeah, both like s of delta and absolute delta will just both be positive. So it's clear that this is true in that case. All right, granted, that wasn't the clearest explanation, but the point is that this term here, including the absolute value sign, can be bounded by the absolute value of delta, this inequality, less than or equal. Okay? So yeah, this term here, or this factor, is less than or equal to the absolute value of delta. And it all follows from the estimates we gave previously, in particular this estimate here, just by modifying slightly. All right. Also, notice that this term right here, or this factor, I should say, including the absolute value sign, is at most 1. Now that, it's clear, and I never really explicitly stated this. I mean, I could state it right now, that the absolute values of all capital C values are at most 1, and similarly, the absolute values of the capital S function are at most 1. So in other words, the range of the capital C function is some subset of the interval -1 to 1. Actually, it turns out that the range exactly is that interval. We don't know that yet. But certainly the range of this function is within that interval. All the possible values of C of theta are between -1 and 1. And all the possible values of S of theta are also. Why is that? Well, it's simply because of this Pythagorean identity. You see that this term here, S of theta squared, is non-negative. So the first term, C of theta squared, by itself is at most that much. And that's simply because when you take a quantity and you add a non-negative thing to it, it increases it. So that accounts for this inequality. All right, well, that tells you that C of theta squared is at most 1. And if you then take square roots on both sides, you see what you get is the absolute value of C of theta on that side and then a 1 on that side. So yeah, that's the proof. Okay, so that factor can certainly be bounded beneath 1. Right? Also, similarly, let's see what I want to say here. Yeah, similarly, this factor here is at most 1 by the same exact theorem. And so it all boils down to trying to estimate this factor. I want to get some bound on this factor. And I claim that that factor is at most delta squared. So we have to establish that. But if you put everything together, you'll see that we get the following upper bound. 1 times delta squared plus 1 times the absolute value of delta. And since delta is less than 1, or the absolute value is less than 1, squaring it makes it even smaller. When you take a number less than 1, positive number less than 1, and you square it, it gets even smaller. So this delta squared here is even smaller than the absolute value of delta, because the absolute value of delta itself is less than 1. So I can upper bound further by using the larger term twice. Take the larger of the two terms, which is the absolute value of delta, and just use it twice. That gives an upper bound. And that's just 2 times the absolute value of delta. So our final upper bound is twice the absolute value of delta. But if you go back to what delta means, delta is this thing here. So you see that I've just bounded the original quantity we started with. We've just managed to bound it beneath 2 times the absolute value of delta, which is that difference in absolute value. And you see that then, therefore, we have a Lipschitz bound, or Lipschitz inequality, where the capital M happens to be 2, always. Doesn't really depend on theta anymore. The capital M might depend on theta in general for a Lipschitz function. It might differ with different thetas. But this capital M happens to be independent of theta. It just has a universal value, 2, which works for every single theta. Okay? And also notice that the H has a universal value, which is 1. As long as phi differs from theta by at most 1. So phi is in the interval theta minus 1 to theta plus 1. So it turns out that the H and the M are universal in the case of the capital S function. H can be taken as 1, and M can be taken as 2 for every theta. Whereas in general, the M and the H will possibly depend on theta. But so, not only is capital S a Lipschitz function, it's what we can call a uniformly Lipschitz function. Okay, we don't really need that, but it's an interesting fact. The H and the M can be taken to be just constants, universal constants, totally independent of theta. But yeah, this is the Lipschitz inequality right here. It just says that, the absolute difference between f of theta and f of phi, where f happens to be the function capital S, is at most m times the absolute difference between theta and phi themselves. Okay, so that fully establishes the Lipschitz property. But notice we have one task left to do. We haven't dealt with that term. But that's pretty straightforward, I think. I hope. Because we know an expression for c of theta, delta rather. We know it starts out like this. Okay, and we wanted 1 minus c of delta. And so you see what happens is, just plug this expression in. Okay, now we have to be careful with these manipulations because, again, infinite expressions sometimes have weird properties. But in this case, that does work out because you might recall I already talked about this idea that if you have a convergent series, you can multiply it through by a constant. And you can also pull that constant to the inside. The resulting series will converge as well. And its sum will be exactly c times the sum of the original series. So a constant can be moved in or out of an infinite sum, as long as the original series converges. We have to assume that. Okay. And so in particular, I can take this constant to be -1. So what that's telling me is that this -1 factor out here can be moved into every term of this series. So this really is 1 minus 1 plus delta squared over 2 minus delta to the 4th over, sorry, this should be 24. Okay. But is it valid to add this plus 1? So I just proved that it's valid to multiply this. We have a -1 factor out here. But then there's still a plus 1 out here. So is it legitimate to take, so yes, it is legitimate to distribute the -1 factor to every term. But then can I also still add 1 to the whole result by just canceling these two? And the answer is yes, you can just cancel the 1 and the -1. Simply because if you look at the partial sums, basically you're having 1 plus a certain series. Let's say it's like this. And we know that the series converges. So the question is, can I regroup the terms to include the one within the A1, something like that? Is it acceptable to regroup the terms in this way? And the answer is yes. I don't want to belabor this point too much, but basically this expression here in the parentheses is a limit. It's the limit of the partial sums, k from 1 to n, and it's the limit as n goes to infinity. But then you can regard this 1 here as being the limit as n goes to infinity of 1. And then you can take the limit sign out of the two terms. You can just remove the limit sign, because the limit of a sum is the sum of the limits. And then you'll have, that. And then everything is a finite sum. Over here, these are just finite sums, so you can certainly group the 1 with the first term. And that becomes a partial sum of a new series, where the first term is now this group. But you're then taking the limit of that partial sum as the number of terms gets bigger and bigger. And that gives you the sum of the whole full series. So it is valid. It's just seeing that it's valid is a little tricky. Kind of requires these clever little tricky arguments. But yes, it is correct to group these two terms together and cancel them out. And so the result is that 1 minus c of delta, 1 minus capital C of delta, is delta squared over 2 minus delta to the fourth over 24, etc. Okay. Let me just write a couple more terms. Okay, well, you see that if I group the terms in twos now, we've gone through this argument several times, this group is negative, and the next group will be negative, and so on. So the result is less than delta squared over 2, which is certainly less than delta squared. Well, less than or equal, because delta could be 0. Okay. Anyway, so that's the complete proof of that. Oh, I'm sorry, I'm being a little bit careless, because I was supposed to prove that, like, it's the absolute value of 1 minus c of delta that's less than or equal to delta squared. So what happened to the absolute value sign? Okay, well, the answer is it's just not necessary. The absolute value sign is not necessary. Because you can see that this is a positive expression, and therefore it's equal to its own absolute value. All right, how can you see that it's positive? You can see it's positive by grouping the terms in twos this way, and then all these groups are positive. Okay, so I'll just let you stare at that and see that it's correct. It's easy to supply the details. Okay, good. So because this difference is already positive in value, it just coincides with its own absolute value, and therefore that justifies that final bound. Okay, good. So we've now fully proven the fact that it's a Lipschitz function, the capital S function, that is a Lipschitz function. And then I just want to tell you why, if f from the reals to the reals is Lipschitz, and let's say f of a is positive and f of b is negative, where a is less than b. So the picture is f of a has a positive height, and then f of b has a negative height, and a is less than b. So a is to the left. Okay, then the claim is that there exists a leftmost or least real root, let's call it c, between a and b, in the open interval between a and b of f. So by a root, I just mean that f of c is 0. But it's least among all roots, at least all roots in that interval. So there may be several roots. See, the graph could look like this, right? Whatever. So there may actually be several roots, even an infinite number potentially in that interval, but there is at least one. And that's what we're looking for. That's going to be called c. Right? So we're going to apply this theorem to the capital S function, and we're going to take a to be 2. So the f will be capital S, which we know is Lipschitz. A will be 2, and b will be 4. So certainly a is less than b. Also, capital S of 2 is positive. Capital S of 4 is negative. So all the conditions are satisfied, and therefore there will exist a least real root between 2 and 4 of the capital S function. And that's what we call pi. So the c in this theorem will be pi by definition. That's how we define pi. Okay? So that'll be like a direct application as a corollary of this theorem. Capital S has a least real root in the open interval 2 to 4. And by definition, we denote it by pi. Okay, so that tells us that S of pi is 0. But it also tells us that, let's just take note of the fact that, in fact, S, capital S function, is actually strictly positive for all theta in the open interval 0 to pi. Okay, let me show you why that's true. This can be sort of a corollary of its own. But we already know that S of theta is positive for all theta between 0 and root 6. All right, and we know that 2 is in this interval. But now what we're saying is that between 2 and 4, there is a leftmost or least root, which is pi. So what that tells you is that between 2 and pi, there are no other roots. Right? Capital S has no roots in between 2 and pi. And that's because pi is between 2 and 4, but it's the least possible root. So between 2 and pi, there are no other roots. Now what I'm going to infer from that is that, in fact, S must be positive when theta is between 2 and pi. Okay, how do I know that? Well, I know that capital S is positive at 2. Right? Capital S, the graph of it, certainly has a positive height at 2. And I know that the height is 0 exactly at pi, because pi is a root by definition of capital S. But how do I know that the graph stays positive, right, between? Right, well, let's ask the question, what if it didn't? What if it went negative somewhere? Well, if it went negative, then it would have to have another root, less than pi, you see, by the same Lipschitz theorem. Everyone follow the argument? You see, if I want to prove that this graph stays above the x-axis until it hits that point, well, assume for contradiction that the graph crosses, or has a negative height somewhere in there. Well, if it has a negative height somewhere less than pi, like somewhere between 2 and pi, then it also has a 0 height. Also, it will have a 0 height. In other words, a root between 2 and pi. But we know that it doesn't. It has no roots between 2 and pi. So you see that it has to stay positive that whole time. And if you put these two facts together, it's positive between 0 and radical 6, and it's also positive between 2 and pi. But those two intervals overlap. 0 to root 6, and then 2 is in this interval, like less than root 6, and then going to pi. So if the function is positive on this interval, and the function is also positive on this overlapping interval, then in fact the function is positive everywhere between 0 and pi, the union of those two intervals. And that's exactly what we wanted here. So that's the proof of that corollary. Okay, and that's an important fact about the sine function, is that it stays positive between 0 and pi. In fact, we know the graph would look something like this. And then it's going to go negative on the other side, right, and come back at 2 pi. But we can talk about that a little bit later. But at least for now, we know that the function capital S stays strictly positive, strictly above the x-axis, when you're strictly between 0 and pi. All right, good. Still have to discuss the existence of this least real root in the general situation of a Lipschitz function. All right, I'm going to give just a sketchy indication. Okay, the idea is, I'll just draw a picture. This argument is a type of argument called repeated bisection. And this type of argument is used to prove a lot of theorems, not just this one. So the technique of repeated bisection is kind of famous piece of mathematics. All right, the idea goes like this. If you look at the midpoint between these, and you just plug that into the function f, there are two possibilities, right? Either you'll get f of this, I'm going to call this midpoint m. Either f of m is greater than or equal to 0, or f of m is negative. Remember that here f of a is strictly positive, and f of b is strictly negative by assumption. So what we're going to do is we're going to choose the interval. Oh yeah, I'm sorry, I screwed this argument up already. My memory is a little iffy. Okay, let me fix. So here's what I want to say. You look at the midpoint m, so that's like a plus b over 2, and you look at the two halves. You have these two halves, right? Now there are two cases that can happen. Either the function f is positive on this entire half, or let's say non-negative on that entire interval. Every point of that interval, the function is greater than or equal to 0. Or the other possibility is that we could have at least one point in here where the function's value, let me call this point x, where the function's value is negative. Okay, so there's a disjunction between these two. One or the other must be the case. Right? Let me call these two cases, case 1 and case 2. Now, in case 1, I'm going to update my interval. Okay, so I need to establish a notation. I'm going to have a sequence of closed intervals, and the initial one, which I'll call I0, is the original interval a to b, closed interval. And now I'm going to update my interval by making it I1 the interval from m to b. In other words, this half. You see, on this entire interval, the function is non-negative, which means that there are no roots. Oh, sorry, I guess I need to say strictly positive. Let me say it's strictly positive on that entire interval. Good. And then here I'll say the f of x is less than or equal to 0, meaning that it's either equal to 0, so there is exactly a root there, or maybe it's less than 0. But the existence of such a point, in other words, is the other case. So in this case, there are no such points. There are no values of x in here where f of x is less than or equal to 0, because the function is strictly positive on that entire half. Okay, yeah, so let me design the cases like that. All right, so yeah, I'm going to update my interval so that I1 is now this half in this case, because the value at m is positive, like f of m, and that's because the value is positive everywhere in that entire closed interval, including at the endpoint, including at m. And so you have the same situation in the small, right, as you did in the large, meaning that the function takes a positive value at this end and a negative value at this end. So that what happens at this end, which is that the function takes a positive value, and what happens at this end matches the behavior originally. So it's like a smaller copy of the original problem. Okay. But in case 2, I'm going to update the interval the other way. In case 2, I'm going to update my interval by choosing I1 to be the first half, a to m. Okay? So it's a dichotomy. I can't tell in advance which case I'm going to be in, but one case or the other must hold. We don't exactly know which in advance, but we know that we'll be in one case or the other. And so we'll have like an I sub 1, okay, in either case. Then we'll just run the same, we'll just loop that. I'll be very informal and just say loop this. Meaning that we then just replace I0 with I1 and start over. Just do the exact same analysis. You look at the midpoint of that. Whatever I1 is, whatever I1 comes out to be, whether it's the left-hand half or the right-hand half, you take its midpoint. Call it like m prime, and just run the same exact argument. And that will give you an updated interval I2. So in this way, we're going to generate a sequence of intervals. Okay. Now, let's take notice of the fact that I1 is just one of the two halves of I0, so it's certainly inside of I0. In other words, I sub 1 is, in either case, inside of I0. Because in case 1, it's like the right-hand half. In case 2, it's the left-hand half. But in either case, it's inside. And the length of it, the length of I1 is just half the length of I0. Okay, by the length of an interval, I just mean like the right endpoint minus the left endpoint, b minus a. Okay, then by the same reasoning, I2 is going to be one of the halves of I1, so therefore inside of that. And the length of I2 is going to be half the length of I1, which is 1/4 the length of the original interval. Okay. Oh, in other words, b minus a over 4. This one is b minus a over 2. And you see that in this way you can generate a whole like nested sequence of intervals. I1 is inside I0, I2 is inside I1, I3 is inside that. So we get this like downward nested sequence where the intervals are shrinking. Each one is inside the one before. And the lengths of these intervals, like they're b minus a over 2 to the n. And that's clearly going to 0 as n goes to infinity. Because the top is a fixed constant, but the bottom is growing arbitrarily large. So these lengths are shrinking like all the way to 0, arbitrarily close to 0. Okay. Good. Now, I claim that these intervals must be closing down on a single point. In the sense that, okay, if I write the nth one of these intervals as like an to bn, in other words, call the left-hand endpoint of the nth interval an, and call the right-hand endpoint of that same interval bn. Well, the fact that we have nesting means that if you look at the nth interval, then you look at the next one is just one of the two halves. So you could have this where the bn plus 1 is the midpoint, so that I sub n plus 1 is inside I sub n. Or the other picture you could have is that maybe it's this half. That's I sub n plus 1. So in this case, a n plus 1 would be here, and b n plus 1 would be here. But you see that in either case, the left endpoints can only ever increase. They can either stay the same. So like in the red case here, the left endpoint stays the same. And in the yellow case, the left endpoint actually jumps ahead to the right. From an to an plus 1 is a jump in the positive direction, toward the right. So the left endpoints can never decrease. They either stay the same, or they increase. Right? And the right-hand endpoints can never increase, because either bn is the same as bn plus 1, or in the other case, bn jumps downward to bn plus 1. So bn can never jump up. Okay? So in other words, what I'm saying is that the a sub n's are increasing, not necessarily strictly. Two of them two consecutive terms could be equal, but they could just never, they can't ever decrease. They can't ever go down. So that's like an increasing sequence, and it's certainly bounded beneath bn, which is bounded beneath b naught, or b, because the b's are going down. Okay, let me draw you the picture. The a's are beginning at a, the b's are beginning at b, and the an's are just moving up, and the bn's are moving down. So any one of the an's is bounded by the corresponding bn, which is bounded by b naught. So you see that the a sub n's are bounded above. and they're increasing, so therefore they converge. They converge to some limit, which let's call C. And this is by the monotone convergence postulate. Remember that any, not necessarily strictly increasing, but just any increasing sequence that's bounded from above must have a limit in the reals by this postulate. Okay. Now, very similarly, the B sub n's are decreasing, and they're bounded below by A. So the monotone convergence postulate also tells us that those B sub n's are converging to some limit, which we can call C prime temporarily. But C and C prime are actually the same, because remember that Bn minus An, which is the length of the nth interval, is going to 0. So, right, Bn can be expressed as An plus their difference, and An is converging to C, and their difference is converging to 0. So therefore, you see that C is equal to C prime. Right, so the intervals are like shrinking down on a common point. The ANs are approaching C, and the BNs are also approaching C. So there is this point C that has that property. C is the common limit of the ANs and the BNs. Okay, now I claim that f of C must be 0. And I claim that, so that's one claim. And then the second claim is that if, let's say, x is between A and C, x is any point strictly between A and C, then f of x is actually strictly positive. So in fact, C is the leftmost root, because anything before C, anything to the left of C, is not a root. F of x will be positive. So this will establish the existence of that, leftmost root that we wanted. Right, so how do I know all this? Okay, well, remember the Lipschitz property. We're going to do this at C. So C has a little interval. C comes equipped with, why? Because it's a real number. C is certainly some real number. So every real number comes equipped with an H and an M in the Lipschitz definition. And as long as I take x within H units of C, but both of these are positive, by the way. As long as I take x within H units of C, then the Lipschitz inequality is this. Okay? And what I'm going to do with that is just plug in like An for x. Okay, but you see that this thing here is going to 0 because the A sub n's are converging to C. So their difference goes to 0. And then this constant m doesn't affect that. If you have a quantity that's going to 0, then m times that quantity will also go to 0. So this side goes to 0, and then 0 is beneath that expression because it's an absolute value. So the Squeeze Theorem tells us that like this goes to 0. And that means that f of An is converging to f of C. And a very similar argument will show that f of Bn is also converging to f of C. Just very similar. Basically, you take the Lipschitz inequality and you just, instead of plugging in x equals An, you plug in x equals Bn. Okay. And notice that Bn is also converging to C. So the same arguments work. Okay, now let's also remember that the way we chose those intervals, we always chose the ith interval, the nth interval, I sub n, such that, let's go back to the original picture. Over here, remember that we choose this half in case 1 because the signs at the endpoints are like a smaller copy of these signs that we had originally. Okay. Now, in this case, down here, case 2, we can't say that because we don't know what's happening at m. What defines case 2 is the existence of this x here, so we really don't know what's happening at m. But we do know that the left endpoint, it will be that. In the updated interval, right? The half we choose is this half. And so its left endpoint the function still takes a positive value there. We just can't say what type of value it takes at m. But certainly takes a positive value at the left endpoint. And that's going to continue to stay true as we subdivide further and further. At the left endpoint, we'll always have a positive value. Okay. So coming back to here, that tells you that the function always must have a positive value at this endpoint for every stage, for every n. In other words, f of An is always greater than or equal to 0. F of An is always greater than or equal to 0 for all n. Okay? But then you can take limits on both sides. Remember that if you have an inequality, if I ever have any inequality between two sequences, like a term-by-term inequality, which holds for all n, and if I know that both sides approach a limit, then the same inequality is true between the two limits. That's a lemma we proved a long time ago. Well, both of these sides have limits. This approaches f of c, according to this, and then 0 approaches 0, obviously, so this must be true. So you see that f of c must be greater than or equal to 0. That's one thing we can certainly conclude. F of c is at least 0. Okay, so to complete the proof, we're going to try to show that if f of c is strictly positive, we get a contradiction. And that means that since f of c is non-negative, but it cannot be strictly positive, f of c has to be 0. Okay, so that's going to prove that c is actually a root. And we'll also talk about why it's the leftmost root in a second. But to even get this, to even show that f of c can't be positive, we need a little bit of discussion. So here's something first. Let's notice that if I take any value of x, like less than or equal to a sub n, so greater than or equal to a, which is a naught, but less than or equal to a sub n, then I claim that f of x must be strictly positive. So the picture looks like this. Here's a, or in other words, a naught. Here's b, or b naught. And the a sub n's like form this increasing sequence. Oh, doesn't have to strictly increase, but generally trends this way. And for any given a sub n, what I'm saying is that all the points in this interval are such that f is positive on that entire interval. And the same is true for any n. So it continues. Like if you look at the next a sub n, the same theorem is true. This fact is true for all values of n. So, you know, also in this interval, the function is strictly positive, and also in the next interval. Right? So I claim that that's true. And that just follows by the way we constructed these intervals. We can sort of picture it like this. We had our original interval, right? And we looked at the midpoint. And then let's just say, for an example, that like f is positive, strictly positive on that entire half. So then we would have chosen I1 to be that half. Now let me just kind of blow that up. We look at the midpoint of that half. If it so happens that the function is positive here, then this would have been I2 by the same process. So you see that in that case, the blue interval takes us from A to this midpoint, and then the green interval takes us to there. So if you put those two sets together, you see that the function is actually positive on that entire set. And that's just going to continue. Now, of course, there is the other possibility. Okay, let's say we start with the same picture where the function happens to be positive here. So I sub 1 is still this half. We blow that up. We look at its midpoint. And now let's say that actually there exists some point here, let's say, where the function takes a non-positive value, just at that point. It's like some x where f of x is less than or equal to 0. Okay, so in that case, we would have chosen I2 to be this half. And so like a sub 2 would be the same as a sub 1. See, I1 goes from A1 to B1, and then I2 goes from A2 to B2. But A2 and A1 would be the same in this case, because it's this half. All right, so the function is still positive to the left of A2, because we already know that it's positive to the left of A1, and A2 is just the same as A1. Okay, so you see in both pictures, both alternatives, it's definitely true that the function is strictly positive to the left all the way, from A, right, to the point A2. Sorry, the point A2 in this picture would be here. Yeah, so from A to A2. And then there's nothing special about 2. Right? We just proved with these pictures, since one or the other must happen, we just proved that from A to A sub 2, in either case, the function is positive. Strictly. But of course there's nothing special about this too. You can run the same argument, you know, loop it over and over. And so yeah, the function is actually positive on the interval from A to A sub n for any n. And that's exactly what we're claiming here. Right, so that's that. Now, one thing that tells us is that, in fact, the function is positive for all x from A all the way to C, but not including C. Which means that if we can show that C is a root, right, if we can show, we haven't done it yet, but if we can show that C is a root of f, then it's the leftmost root, because from A, or the leftmost one in the interval, right, in the given interval, A to B. Yeah, because from A to C, in this whole entire half-open interval, the function has a strictly positive value, and then its value is exactly 0 at c. So you see that it's not just a root, it's the leftmost root in that interval. Okay? And why is it true? Well, it's very simple. It's just because the a sub n's are increasing towards c. C is their limit. So if I know that the function is positive on this interval, and I know it's positive on this interval, and on this interval, and on this one, and on this one, and so on, as those points get closer and closer to c, the union of all those intervals is this. So if it's positive on every one of them, then it's also positive on the union of all of them. And so you see what I'm saying is that if I take the interval from a to a sub n closed, but I take the union of all of them, all infinitely many, as n increases, that's just going to give me the interval from a to c, just not including c. The reason it doesn't include c is because the a sub n's are just converging towards c. Okay, now actually, that's not entirely accurate. It could include c. So I have to include both cases, which is symbolized, or at least I do, by this kind of weird hybrid bracket, which is either a closed bracket or an open bracket. C may or may not be included, because you see, one thing that could happen is that the a sub n's might approach c and then reach it in finite time and then stay equal to c forever. So you can imagine like the a sub n's are increasing and then they hit the value c and then they just stay there forever. And then c would of course be in the union. But you see, in that case, it doesn't matter, because certainly this interval where we don't include c is at least a subset of that. Right? Because the answer for this union is either this one that's open at c or one that's closed at c, but in both cases, the one that's open at c is certainly included within. So since the function is positive on every one of these, it's also positive on their union, and therefore it's also positive on any subset of their union. So yes, on this interval, the function is definitely strictly positive. Okay? So that we just managed to prove this. All right, now I still have to show that like f of c can't be positive. And let's just kind of do that with a little picture. So let's say c is here. And let's also recall that in this entire interval, f is strictly positive, as we just showed. Just we don't know what happens at c. We do know that f of c is at least 0. We have proven that. But you see, this leaves two possibilities. Either c is a root, or f of c is strictly positive. And we have to investigate this and show that it's impossible. It should lead to some contradiction. Right? So let's assume it. Let's assume f is strictly positive here. Okay. Now, by the Lipschitz property, that's going to tell us that there's some interval around c where f is positive also. There's some interval centered at c, such that f is positive in that entire interval. Okay, and that interval will have a positive length. And the reason for this is, if you look at the Lipschitz inequality, you see that what it's basically telling you is that if x is very close to c, so that this difference is very small, and then m is just a constant, so it's not going to make that much difference when you multiply by m. This whole thing is going to be very small. And so f of c and f of x have to be very close together, because their difference is small. Their difference is less than or equal to some very small quantity. And you can make it as small as you like by taking x to be very close to the point c. And so by restricting x very close to c, let's say from c minus epsilon to c plus epsilon, where epsilon is some tiny positive number, right? We can make this side less than like m times epsilon. Actually, maybe I'll do it this way. Like, instead of using epsilon here, I'll use epsilon over m. And then this side is just going to be less than epsilon. Epsilon can be like arbitrarily small. All right, so you see that I can make this difference as small as I please. And because f of c is positive, it means that f of x has to be positive too, since they differ by a very tiny amount. Yeah, like if you think about a number line, if f of c is some positive number, and f of x is very close to that number, then no matter if f of x is here or here, it's still going to be positive if f of c is positive. Okay? As long as the difference between the two is small enough. How small does that difference have to be? Well, that difference has to be less than the absolute value of f of c itself, which is this distance. Right? As long as the distance between these 2 points is less than that red distance, then this will be true, that f of x will have to be positive as well, because you see that it's on the positive side of 0. And we can arrange for that to happen just by choosing this epsilon sufficiently small. Namely, how small do we need the epsilon? Well, we just need it to be this. Okay, so we just choose the epsilon to be that. And then the conclusion is that f of x will have to be positive as long as x is in this interval. C minus epsilon over m to c plus epsilon over m. Okay, so there's this little interval around c that has a positive length, where the function is strictly positive, f of x. For all x's in that interval, f of x comes out strictly positive. Okay, now what's the relevance of that? Well, I claim that in the process of repeated bisection, because the function is positive, in fact, now you see from all the way from a to this point. Okay, my diagram is like seriously cluttered, but the function is actually positive on this entire interval here, because we know that it was positive from a to c, just possibly not including c, but we also know that it's now also positive on that little green interval. So in fact, we know that it's positive on this red interval here, all the way. All right, now in the process of subdivision, what that tells us is that the a sub n's would move past c. The a sub n's would like increase this way, and they would eventually surpass the point c, just by the nature of the construction. You have to think about that a little bit. The way we constructed that nested sequence of intervals is such that, you know, if the function is positive in some interval, strictly positive, let's say, right? So what happens is then that as you're bisecting, so like the first midpoint is here and the function is positive, so we would choose this interval next. Then what happens? Well, we look at this next midpoint. And, you know, if the function is positive here, we would choose this next. But then you see that one of the endpoints would have surpassed x. Okay, now, it's also possible that maybe the function is not positive all the way from here to here. Maybe it takes a negative values like somewhere here. A negative value or maybe 0. So what would happen in that case? See, all I'm assuming is that it's positive like up to x. Up to x. But beyond that point, maybe it could take the value 0 eventually, or some negative value. Right? But then what would have happened is that the a sub n's would have just frozen for a while, not increased anymore. So in other words, instead of this half being selected, in that case, this half would have been selected. So the half chosen previously was this one, and then the new one is this yellow one. They have the same left endpoint. So, like, you know, the a sub n sequence, which are the left endpoints, would have just like stayed still for a while, having repetitions, consecutive terms equal. But then the intervals are halving in length every time. So eventually, the intervals will get short enough so that, like, if the next one is this half, then the function is positive on that one, on that half, which means that actually we wouldn't have selected that half. We would have really selected this half. So that's another jump. And you see, that jump takes you closer to x. But by this process, sorry, I guess I really want to say that the function is positive like beyond x. The function is positive up to x and also a little bit beyond x. Let's say that. Okay. Well, then the a sub n sequence will eventually surpass x. So if I assume that the function is positive like in this interval, kind of beyond x, right? So after our first subdivision, let's say the midpoint is here. So since the function is positive on this half, we would have selected this half as our I1. Now, when you look at the next midpoint, if the function happens to be positive all the way over here, then we would have selected this, which means that the a sub n sequence jumps past the x, because the a sub n sequence jumped from this point to this point. That is the left endpoint, right? The left endpoint of this blue interval is here, and the left endpoint of the yellow one is here. So it like already jumps past x. But the other thing that could happen is maybe the function is not positive all the way up to here, because maybe there could be a point in here where the function is negative or 0. Let me just denote that as like a question mark. So that would not be the case. Then we wouldn't select for the yellow interval, we wouldn't have selected this one. We would have selected this one. Okay, then we would have split that. But you see now, function is positive in that first half. So the next selection would have been that. And you see that again, the left endpoint has already surpassed x. Eventually that will always happen. the left endpoint sequence will surpass that value. All right, so if we apply that insight here, because the function is now known to be positive on this entire red interval, which goes past the value c, then the a sub n sequence would have surpassed c by the way it's constructed. But you see, that's impossible, because the a sub n's are increasing and they're approaching c. The only way that can happen is if they're always less than or equal to c for all values of n. So there's no way that... Okay, at any rate, that's the proof of that theorem. Perhaps not explained as well as possible, but we can let that point go. All right, well, the last thing for this video is the following theorem. So first of all, let's prove that capital C of pi is -1, and then capital S of pi is 0. And let's also prove that capital C of 2 pi is 1. Capital S of 2 pi is 0. And then we also have these periodicity laws, where if we add 2 pi to the input, it doesn't change the value of either capital C or capital S. Okay, so this is a very important general law called the periodicity law. And so what it says is that the capital C function is periodic with a period of 2 pi, and same for the capital S function. Right, these also are special values that are useful. Values at pi, and then the values at 2 pi. And all of these are considered part of trigonometry. Okay, well, all of these are very, very easy to get now. Basically, we already know that S of pi is 0, because pi was defined that way. And so remember that pi is defined as the least real root of the function s in the open interval 2 to 4. Right? But we also know that since capital S is positive on 0 to 2, inclusive of 2, that in fact pi can be described as the least positive real root. That's probably a nicer way to describe it. It's the least positive real root of the capital S function. So, but in particular, it is a root, so we know this. Right? And then the only question is, like, how do I know that the cosine, or the capital C function, has the value -1 there? All right, well, one thing you can definitely see, if you look at the Pythagorean relation at pi, so we know that S of pi is 0, which means this whole term zeroes out, and therefore C of pi squared is 1. And it follows that C of pi itself is either 1 or -1. Okay, now we need to eliminate 1 as a possibility. So let's suppose, for contradiction, capital C of pi is 1. Well, it would follow that e to the I pi yeah, it would follow that e to the I pi, which has this expression, right? This would be a 1, and this would be a 0. So we just get 1. Now we can square. No, that's not what I want to do. Sorry, here's what I really want to do. I want to consider e to the I pi over 2. So pi is just some real number. Pi over 2, some real number. But if we square this, that's just the product, right? But we have a lemma that we proved that says that basically e to the I theta times e to the I phi is e to the I times theta plus phi. So if we use that lemma here, we just get e to the I times pi over 2 plus pi over 2. In other words, e to the I pi, and we know that that's 1 from here, right? According to our assumption. We're supposing right now. So according to that supposition, we should get 1. But here's the problem with that. The only solutions of z squared equals 1 in the complex plane are just 1 and -1. And you can easily see that just from factorization. See, z squared equals 1 is equivalent to z squared minus 1 equals 0, which can be written equivalently as like z minus 1 times z plus 1 equals 0. And the only way that you can get a 0 product is if one of the factors is 0. So either z is 1 or z is -1. So 1 and minus 1 would be the only two possibilities. That would lead us to conclude that e to the I pi over 2 is either 1 or minus 1. But either way, it's real. And if we write it in terms of its real part and its imaginary part, the fact that this is a real number tells us that the imaginary part would have to be 0. So in other words, we would conclude that s of pi over 2 is 0. But you see, this is a contradiction because in fact s is known to be strictly positive for all theta in the interval 0 to pi. And pi over 2 is certainly in that interval. So yeah, s of pi over 2 is supposed to be positive in particular, right, by this general fact. So we have a contradiction. On the one hand, s of pi over 2 is 0. On the other hand, it's positive. Okay, and these clash. So our original supposition, which was this, has to be wrong, has to be rejected. And therefore, the only possibility from here is -1. So yeah, we can conclude that c of pi is -1. Okay, and that proves the first theorem. And now the others are easy to get. So for example, c of 2 pi, we can just think of it as pi plus pi. It's like a double angle formula. In fact, I may as well just cite a double angle formula as a theorem. We've already derived them. So, for example, like s of 2 theta is 2 s of theta c of theta. And then c of 2 theta was c of theta squared minus s of theta squared. And there are two alternative forms of that, which we also have encountered. Well, we looked at one of them. The other one is very similar, has a similar proof. Okay, so these are called double angle formulas. And I'm sure you've seen them before. And you see that the cosine function has 3 distinct double angle formulas, each of which is useful in its own context. But anyway, from double angle formula, we see that this is like c of pi squared minus s of pi squared. And s of pi is 0. C of pi is -1. You have to square that. So you get 1. As far as s of 2 pi, like the double angle formula there tells us this. And, remember that this is 0. That's -1. So the whole product, again, comes out to 0. So that proves the values at 2 pi. Okay, as for the periodicity, that's just based on the addition law. See, if I want cosine of, for example, c of theta plus 2 pi, what I can do is just the c value times the other c value minus the s value times the other s value. But recall that this is 0. And also recall that this is 1. So in the end, you just get c of theta times a 1, right, minus a 0. And then similarly for this one, it's like s of the first, c of the second, plus c of the first, s of the second. That's 0, and that's 1. So we just get s of theta. Okay, so good. That proves basically all the laws of trig. With the laws that we've proven so far, we've now got enough information to just derive every other trigonometric identity. So at this point, we're fully justified in writing capital C as cosine and writing capital S as sine. We've recovered, in other words, all the familiar properties of those two functions that those two functions are supposed to have, including the geometric interpretation. So, okay, I'm going to conclude this video here. I'm sorry it went on quite so long. And in the next part, the final part, we will talk about the arctangent function and the solution to the problem of like finding the radian measure of an arbitrary angle. Okay, so that'll be part 5 and the final part of this unit. Okay, take care, guys.